Welcome to Science, to Sleep By, the place where the mysteries of the universe unfold gently as you drift into rest. Tonight, we're going to explore one of the most fascinating questions in physics. Why does light have a speed limit? Light, the fastest traveler in the cosmos, moves at nearly 186,000 miles per second. But why not faster? Why is there a cosmic speed cap at all? As you settle in, let's journey through space, time, and the fabric of the universe together, uncovering the secrets of light's limit in a way that both calms the mind and sparks wonder. To begin understanding why light has a speed limit, we first need to step back and reflect on what light truly is. For centuries, human beings have stared at the night sky, amazed by the shimmering stars, and wondered what this radiant phenomenon was made of. The glow of a candle, the warmth of the sun, the flicker of fireflies in a dark summer evening, all of these experiences have carried the same mystery. Light is so familiar that we often take it for granted, yet its nature is far from simple. In fact, light is one of the most fascinating and complex phenomena in all of physics, occupying a place at the very heart of how the universe works. When scientists describe light, they often say that it is both a wave and a particle, two identities that coexist in a delicate balance. This idea may sound contradictory at first, but it's one of the most extraordinary truths we've uncovered about nature. Light behaves like a wave, spreading out, bending around objects, and interfering with itself, much like ripples that travel across the surface of a pond. This wave-like behavior allows it to display patterns of color, refraction, and diffraction, creating everything from rainbows in the sky to the dazzling patterns of light scattered on water. Yet light is not just a wave, it is also a particle, carried in tiny packets of energy called photons. These photons have no rest, mass, and yet, they are brimming with energy, capable of illuminating worlds, powering plants through photosynthesis, and fueling the technology of lasers, solar cells, and fiber optics. This dual identity is known as wave-particle duality, cornerstone of quantum mechanics. It tells us that light cannot be boxed into a single description, because its behavior depends on how we interact with it and measure it. When we observe light in certain experiments, it appears as a continuous wave, oscillating in electric and magnetic fields. In other settings, it reveals itself as individual photons, discrete quanta that strike detectors one by one. This duality is not just a curiosity, it's the key to why light behaves the way it does, and why it travels at the speed it does. But what exactly makes up a wave of light? Light belongs to the family of electromagnetic waves. Unlike sound waves, which need air or some other medium to travel through, light is self-sufficient. It consists of oscillating electric and magnetic fields, dancing in perfect harmony, perpendicular to each other and to the direction in which the light moves. Because of this, light can travel through the vacuum of space, carrying energy from the sun across 93 million miles to Earth, illuminating our days and sustaining life. Without this ability to move through emptiness, our planet would be cold and lifeless, isolated from the energy that drives weather, biology, and growth. The understanding that light is an electromagnetic wave was a tremendous breakthrough in the 19th century, largely thanks to the work of James Clerk Maxwell. His equations showed that changes in electric and magnetic fields could sustain each other, producing a self-propagating wave that moves through space at a fixed speed. And when Maxwell calculated that speed, he discovered something astonishing. It was the same speed that had already been measured for light itself. Suddenly, light was no longer just a mystery of vision or a property of fire. It was the visible part of a vast electromagnetic spectrum, stretching from radio waves on one end to gamma rays on the other. Light, in other words, was woven into the very fabric of electromagnetism, one of the fundamental forces of nature. For everyday life, we experience only a narrow slice of this spectrum, known as visible light. Our eyes evolved to detect wavelengths from about 400 to 700 nanometers, giving us the colors of the rainbow. But beyond this lies infrared light, which carries heat, ultraviolet, which can cause sunburns, X-rays, which let doctors see inside the human body, and radio waves, which carry music, conversations, and data across the air. All of these are light, all of them electromagnetic waves, and all of them travel at the same fundamental speed in a vacuum. This universality is part of what makes light so central to physics. It doesn't matter what frequency or wavelength it has. The speed is always the same. Still, what makes light so remarkable is not just its structure as an electromagnetic wave, but also its quantum side. When viewed as photons, light is energy without rest mass. This absence of mass is what allows photons to travel at the maximum cosmic speed. Unlike particles with mass, which need to be pushed and fueled to accelerate, photons are born moving at light speed. It is built into their nature. They do not speed up or slow down, they always move at exactly the same pace. 299,792,458 meters per second. This number is not arbitrary. It is the result of the very structure of the universe, tied to the way space and time themselves are woven together. To appreciate the role of light in the cosmos, think about what happens every time you see something. When you look at the moon on a quiet night, the light entering your eyes left that lunar surface just over 1 second ago. When you gaze at the sun, you are seeing light that left it about 8 minutes earlier. The stars above are even more profound. Many of them shine from hundreds, thousands, or even millions of light years away. That means the light entering your eyes tonight may have started its journey before the rise of human civilization, long before the pyramids were built, long before humans learned to write. In this way, light is not just an electromagnetic wave or a photon. It is a messenger, carrying information across vast stretches of space and time, delivering to us the story of the universe's past. The storytelling ability of light is only possible because of its unchanging speed. If light could travel at different rates, the universe would appear distorted, scrambled, or unreadable. Instead, light's constancy allows astronomers to measure distances, map galaxies, and calculate the age of the cosmos. By studying the faint afterglow of the Big Bang known as the cosmic microwave background, scientists can peer back nearly 14 billion years. All thanks to light traveling faithfully at its cosmic speed limit. Light also interacts with matter in ways that make life possible. Plants capture light through photosynthesis, transforming photons into chemical energy that becomes the foundation of the food chain. Human technology, too, relies on light's properties. From the lasers that scan barcodes and perform delicate surgeries, to fiber optic cables that transmit information across continents, carrying voices, videos, and data streams that knit the modern world together. Even your ability to listen to this very speech relies, in some indirect way, on the power of light and its interactions with matter and energy. Understanding the nature of light is the first step in understanding why it has a speed limit. It is not just a glow in the darkness, not just a phenomenon of sight, it is a fundamental expression of the laws of physics. Light is woven into the fabric of electromagnetism, shaped by the geometry of space and time, and governed by the deep principles of relativity and quantum mechanics. Its dual identity as both wave and particle makes it one of the most mysterious and essential features of reality. To know why it cannot go faster, we must first appreciate what it is, how it travels, and why its speed is inseparably tied to the structure of the universe itself. When we talk about light, one of the most awe-inspiring aspects is its speed. Light does not creep across space like a wandering traveler. It blazes with unimaginable swiftness, crossing vast cosmic distances in the blink of an eye. For most of human history, people assumed that light was instantaneous, that it simply appeared the moment a source was revealed. Philosophers debated whether it was a substance traveling across space, or whether it simply manifested in the eye. It wasn't until the 17th century that humanity began to grasp that light actually had a finite speed. And what we discovered was something extraordinary. Today, we know with great precision that the speed of light in a vacuum is exactly 299,792,458 meters per second. In terms more familiar to everyday life, that's about 186,000 miles per second. To put that in perspective, light can circle the Earth more than 7 times in just 1 second. It can travel from Los Angeles to New York in less time than it takes to snap your fingers. This speed is so immense that our brains struggle to truly comprehend it, and yet, it is not infinite. It is a number, a constant, a cosmic boundary written into the structure of reality. The story of how this value was determined is itself a testament to human curiosity and ingenuity. In the 1600s, Galileo tried to measure the speed of light by using lanterns and shutters, signaling with an assistant stationed on a distant hill. The idea was to open one lantern, and when the assistant saw it, they would open theirs in return. Galileo hoped to measure the delay, but the distances were too small and human reaction time too slow. To him, light seemed instant. But soon after, the Danish astronomer Ole Remer provided the first evidence that light did indeed have a finite speed. While observing the moons of Jupiter, he noticed that the timing of their eclipses shifted depending on Earth's position in its orbit. When Earth was moving away from Jupiter, the eclipses appeared later than expected, and when moving closer, they appeared earlier. Remer realized that this effect was due to the finite speed of light, which required extra time to cover the changing distance. His measurements were not exact by modern standards, but they were revolutionary. They showed that light had a measurable velocity. Later experiments refined this value further. Hippolyte Fizeau, in 1849, used a rotating toothed wheel and a beam of light reflected from a distant mirror to measure the delay caused by the finite speed of light. Éliane Foucault improved the method with rotating mirrors, and with every refinement, the number became clearer. By the time of Albert Michelson in the late 19th century, precision had increased to an extraordinary level. Michelson's experiments with rotating mirrors and long baselines confirmed light's velocity with remarkable accuracy, work that would later earn him the Nobel Prize in Physics. What makes the speed of light so remarkable is not just its size, but its universality. Unlike the speed of a car, a plane, or even sound, the speed of light is not dependent on the motion of its source. If a car speeds down the highway and shines its headlights, the light doesn't travel faster because the car is moving, it still travels at the same cosmic constant. This universality was one of the great puzzles of the 19th century. As scientists struggled to reconcile Maxwell's equations of electromagnetism, which predicted a fixed speed of light, with the idea that speeds should add together in ordinary motion, the answer came with Einstein's theory of special relativity in 1905. Einstein realized that the speed of light is not just another speed. It is the ultimate speed limit of the universe, a constant that is the same for all observers, no matter how fast they are moving. This realization overturned centuries of assumptions about space and time. No longer were they absolute and changing backdrops. Instead, they were flexible, intertwined, and relative, but always bound together by the constant of light's velocity. To see how powerful this idea is, consider how we measure distances in the universe. On Earth, we talk in miles or kilometers, but for astronomy, those units quickly become impractical. The universe is simply too vast. Instead, astronomers use the concept of a light year, the distance light travels in 1 year. That's about 6 trillion miles. When we say a star is 10 light years away, we mean that the light we see from it tonight actually began its journey 10 years ago. When we look at the Andromeda galaxy, more than 2 million light years away, we see it not as it is now, but as it was 2 million years in the past. The speed of light is not only a number, it is a cosmic ruler, defining how we experience distance and time on the grandest scales, even in everyday life. The speed of light defines the limits of communication and technology. Fiber optic cables carry pulses of light across continents, connecting voices and data around the world. Satellites orbiting Earth relay signals that depend on the predictable travel time of light. Even when you make a video call, there is a tiny delay, often imperceptible, caused by the finite speed of signals traveling as light through fiber and across space. The speed of light is so fast that we rarely notice these effects, but they are always there, reminding us that information, no matter how advanced our technology, cannot outrun this cosmic cap. The importance of defining light speed goes even further. In 1983, the international scientific community decided to fix the value of the speed of light as an exact number, 299,792,458 meters per second, and to use it as the foundation for defining the meter itself. Instead of measuring light speed, we now define our units of length based on it. This shows just how deeply light speed is woven into our measurement systems, into the very way we quantify reality. It is not simply a physical phenomenon but a standard, a benchmark that underpins science, engineering, and communication across the globe. But why this number? Why not faster or slower? This is where the deeper mysteries lie. The speed of light is not just an arbitrary figure. It emerges from the relationship between electric and magnetic forces. Maxwell's equations predict that electromagnetic waves travel through a vacuum at a speed determined by the electric permittivity and magnetic permeability of free space. These constants describe how electric and magnetic fields interact in the void, and when combined, they yield precisely the value we recognize as the speed of light. It is, in other words, built into the very structure of the universe, a product of the properties of space itself. This constant speed has profound consequences. It means that the laws of physics are the same everywhere in the universe, that causality is preserved, and that no signal, object, or particle with mass can outrun light. It sets the stage for relativity, for the bending of space and time, for the way we experience time dilation and length contraction at high velocities. It defines the horizon of what is possible in communication and travel. It anchors our understanding of black holes, cosmology, and the birth of the universe. Without this constant, the universe would be chaotic, unpredictable, and unrecognizable to us. So, when we define the speed of light, we are not just assigning a number to a familiar phenomenon. We are recognizing the deep structure of reality, the fabric that holds together space, time, energy, and information. It is a speed that is not merely fast, it is fundamental, universal, and unchanging. It is the speed at which the universe itself communicates, the pace at which the story of the cosmos unfolds across billions of years and billions of light years of distance. When we try to answer the question of why light has a speed limit, one of the most important breakthroughs we must explore is Albert Einstein's theory of relativity. This idea, introduced in 1905 and expanded in the years that followed, completely reshaped our understanding of space, time, motion, and the laws that govern the universe. Before Einstein, physics was built on the foundations of Newtonian mechanics, which described motion, forces, and gravity in terms of absolute space and absolute time. In Newton's universe, time ticks steadily for everyone, like a universal clock, and space was an infinite, unchanging stage on which events unfolded. But experiments in the late 19th century, particularly those involving light, began to reveal cracks in this classical picture. The behavior of light did not seem to fit neatly into Newton's framework, and a new way of thinking was needed. Einstein's insight was both simple and profound. The speed of light in a vacuum is the same for all observers, regardless of how fast they are moving or what direction they are traveling. This might sound straightforward, but it was revolutionary. To see why, consider the everyday world. If you are riding in a car moving at 60 miles per hour and you throw a ball forward at 30 miles per hour, someone standing by the roadside would measure the ball's speed as 90 miles per hour. Speeds add together in ordinary experience. But light refuses to play by these rules. If you shine a flashlight while riding in that same car, the light beam will still be measured by an observer outside as traveling at 186,000 miles per second, not 186,000 plus 60. The speed of light remains constant, no matter how you try to chase it or outrun it. This constancy of light speed forced Einstein to abandon the notion of absolute space and time. Instead, he proposed that space and time are interwoven into a single continuum called spacetime, and that measurements of distance and duration depend on the relative motion of observers. This is the essence of special relativity. In this framework, two people moving at different speeds may disagree on how long an event lasts or how far apart two points are, but they will always agree on the speed of light. Light becomes the anchor that holds the structure of spacetime together, the one constant that does not shift no matter what. One of the most famous consequences of relativity is time dilation. Imagine two twins, one staying on Earth, and the other traveling through space at a speed close to light. For the traveler, time will pass more slowly relative to the twin who remained behind. If the traveler returns after what felt like a few years to them, they might find that decades have passed for the twin on Earth. This is not science fiction. It is a direct consequence of the geometry of spacetime and has been confirmed in experiments using fast-moving particles and highly precise atomic clocks. Another consequence is length contraction. Objects moving close to the speed of light appear shortened along the direction of motion to an outside observer. From the perspective of the moving object, nothing unusual happens, but to someone watching from another frame of reference, distances shrink. Again, this effect has been confirmed experimentally, demonstrating that space and time are not fixed but flexible. Responding to the relative motion of observers, Einstein's theory also revealed a deep connection between mass and energy, captured in the famous equation E=mc. This relationship tells us that mass is simply another form of energy, and the speed of light squared acts as the conversion factor between the two. The equation not only explains why nuclear reactions release enormous amounts of energy, but also underscores the fundamental role of light speed in the laws of physics. The presence of c in the equation shows how deeply the speed of light is tied to the very structure of energy and matter in the universe, but relativity goes beyond just special relativity. A decade after introducing his first theory, Einstein expanded it into what is known as general relativity. In this broader framework, gravity is no longer described as a force pulling objects together, as Newton suggested, but as the curvature of spacetime itself, caused by mass and energy. Massive objects like stars and planets bend the fabric of spacetime, and light follows these curves, creating phenomena such as gravitational lensing, where the path of light from a distant star or galaxy is bent around a massive object in the foreground. Once again, the speed of light plays a central role. Because it is the ultimate speed at which information and influence can travel through spacetime, relativity also imposes a profound restriction. Nothing with mass can ever reach or exceed the speed of light. As an object with mass accelerates, its energy increases, and the closer it gets to light speed, the more energy is required. To actually reach the speed of light would require infinite energy, which is impossible. This is why photons, which are massless, are the only particles that can naturally travel at light speed. It is their lack of rest mass that frees them to move at the maximum pace allowed by the universe, while everything else must remain slower. The implications of relativity are staggering when applied to the cosmos. The finite speed of light means that we look into the past whenever we look into the night sky. It means that nothing can signal or travel faster than this cosmic limit, preserving the cause and effect structure of the universe. It ensures that events unfold in a consistent order, preventing paradoxes where an effect could precede its cause. Without relativity's rules, the universe might not make sense at all. Relativity also helps explain phenomena such as black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. At the event horizon, the boundary of a black hole, the escape velocity equals the speed of light. Beyond this point, the warping of spacetime is so extreme that all paths lead inward, and light itself is trapped. Once again, the speed of light emerges as the critical threshold, marking the boundary between what can communicate with the outside universe and what is forever sealed away. In the centuries since Einstein first proposed relativity, countless experiments and observations have confirmed its predictions. From the bending of starlight observed during solar eclipses to the precise functioning of GPS satellites, which must account for both special and general relativistic effects to provide accurate navigation, relativity has become one of the most thoroughly tested theories in science. Its success lies in the way it incorporates the speed of light as a universal constant, a principle that reshapes space and time themselves, rather than being bent to fit them. for a US audience. It is worth noting that much of the pioneering experimental work in relativity was carried out by American scientists. Albert Michelson, who made some of the first highly accurate measurements of light speed, worked in the United States and became the first American to win a Nobel Prize in science. The verification of relativity's predictions, from astronomical observations to particle accelerator experiments, has been a global effort. But the United States has played a central role in pushing the boundaries of these discoveries. Relativity is not just a European or theoretical idea, it has become part of the shared scientific heritage of humanity, with practical implications felt in everyday American life. From the synchronization of communication systems to the exploration of space, the theory of relativity is much more than an abstract piece of physics. It is a window into the deep structure of the universe, a framework that explains why light has a speed limit and why that limit defines the very fabric of reality. It tells us that space and time are not rigid backdrops, but dynamic, interconnected dimensions shaped by motion, mass, and energy. It shows us that light's speed is not a trivial feature, but the foundation of cosmic order. And it reminds us that even the most ordinary observations, the shining of a flashlight, the ticking of a clock, the image of a star, are woven into a tapestry of profound and elegant laws that govern all of existence. To understand why light has a speed limit, we must take a closer look at the fabric that underlies all of existence, spacetime itself. This idea may sound abstract at first, but it is central to modern physics, and it is where the true relationship between light and the cosmos is revealed. When Albert Einstein introduced the concept of spacetime, he was not merely adding a new term to physics. He was showing us that space and time, which for centuries had been thought of as separate, absolute entities, are in fact deeply interwoven into a single, four-dimensional continuum. And at the very heart of this continuum lies the speed of light, not as a simple property of photons, but as a defining feature of reality itself. Spacetime can be imagined as a kind of fabric, stretching across the universe, with every point representing a location in space and a moment in time. Just as a piece of fabric can be bent and stretched, spacetime is not rigid. It is influenced by mass, energy, and motion. What Einstein showed is that the speed of light is not merely a number imposed on the universe, but a fundamental consequence of this fabric's geometry. Light's velocity is baked into the very equations that describe spacetime. To begin seeing this connection, consider how we measure distances and times. In everyday life, we think of them as separate, miles and minutes, feet and seconds. But in spacetime, distance and time are combined into a single entity. Events are separated not just by how far apart they are in space or how long apart they are in time, but by a unified measure called the spacetime interval. This interval is what remains consistent for all observers, no matter how they move, and it is built upon the constancy of the speed of light. In mathematical terms, the speed of light acts as a conversion factor between space and time. Because light always moves at the same velocity, it creates a bridge between how we measure distance and how we measure duration. 1 light second, for instance, is both a measure of distance, the length that light travels in 1 second, and a measure of time itself. By tying these together, the speed of light becomes more than a property of photons. It becomes the scaling constant of the universe, the rate at which space and time are stitched together. Without it, the fabric of spacetime would unravel into something incoherent. One way to visualize this is with what physicists call the light cone. Imagine a single flash of light emitted from a point in spacetime. The light spreads outward in all directions, forming a cone when drawn in a diagram that shows time moving upward and space spreading outward. This cone represents all the places that the light can reach in the future, and all the places from which light could have arrived in the past. The surface of the cone is traced by the paths of photons, always moving at the speed of light. Inside the cone lies the region where cause and effect can operate, where signals can pass and influences can travel. Outside the cone, however, is forbidden territory, regions that cannot affect or be affected by the event, because doing so would require something to move faster than light. In this way, the structure of spacetime itself enforces the speed limit. It tells us what events can be connected and what events remain forever separate. The light cone also explains why faster-than-light travel leads to paradoxes. If something could move outside the cone, it could effectively jump between points in spacetime in ways that might allow an effect to precede its cause. Imagine receiving a message before it was ever sent, or seeing an explosion before the bomb was ignited. Such violations of causality would unravel the logical order of the universe. But because the speed of light defines the boundary of the cone, spacetime protects causality by ensuring that all influences remain inside the proper limits. It is also fascinating to consider how the curvature of spacetime affects light itself. In the presence of mass and energy, spacetime is warped, and light follows the curves of this warped geometry. This is why starlight bends around the sun during an eclipse, an effect first observed in 1919 and one of the earliest confirmations of general relativity. To us, it may look as though the light is being pulled by gravity, but in Einstein's description, it is simply traveling along the straightest possible path through curved spacetime. Once again, light reveals its intimate connection to the structure of the cosmos, moving not just through space and time, but through the very geometry that defines them. Another way to appreciate the role of light in spacetime is to consider what would happen if its speed were different. If light were infinitely fast, then all events in the universe would be instantly connected. Space and time would collapse into a meaningless jumble, with no distinction between here and there, now and then. If light were slower, the structure of spacetime would stretch differently, and the scales of causality, distance, and time would be altered in ways that might not allow the universe as we know it to exist. The exact speed of light we observe is not arbitrary. It is a reflection of the fundamental constants that define the geometry of reality. Spacetime also dictates how observers moving at different velocities perceive the world. Thanks to relativity, one observer's present may not match another's, depending on their motion. Yet despite these differences, the speed of light remains the same for both. This constancy anchors the shifting perspectives of observers into a coherent framework. It ensures that while space and time may stretch and bend, the fabric does not tear. It is the cosmic stitching that holds the quilt of reality together. For a US audience, it may help to think of spacetime and the speed of light in terms of navigation and communication, areas that touch everyday life. Consider the satellites in the Global Positioning System. These satellites orbit Earth while broadcasting signals at the speed of light. For GPS to work, the system must account for the effects of relativity. Because the satellite's clocks tick slightly differently from clocks on Earth, due to both their motion and their position in Earth's gravitational field. Without correcting for these relativistic effects, GPS would drift off by miles within a day, making navigation unreliable. The success of GPS is a direct demonstration of how the structure of spacetime and the speed of light affect practical technology in the modern world. Astronomers, too, rely on the speed of light as the ruler of spacetime. When measuring the distance to stars, galaxies, and the farthest edges of the observable universe, light serves as both the messenger and the yardstick. The finite speed means we see celestial objects as they were in the past, not as they are now. This delay is not a flaw, but a window, allowing us to peer back into the history of the cosmos. By studying light from distant galaxies, we can reconstruct how the universe evolved, how stars and planets formed, and how spacetime itself has stretched and expanded over billions of years, at the largest scales. The interplay of light and spacetime defines the horizon of the observable universe. There is a boundary beyond which light has not had enough time to reach us since the beginning of the cosmos. This boundary, called the cosmic horizon, marks the edge of what we can ever see. It is not a physical wall, but a limit imposed by spacetime itself. Light's finite speed creates this horizon, shaping the scope of our cosmic vision. Beyond it, the universe may continue endlessly, but it remains forever hidden from us, sealed away by the structure of spacetime and the unwavering law of light's velocity. Even black holes, the most extreme objects in the universe, are defined by the relationship between light and spacetime. The event horizon of a black hole is the boundary where spacetime is curved so steeply that light itself cannot escape. It is the ultimate demonstration of how spacetime and light are bound together. The speed of light marks the dividing line between what remains visible to the universe and what vanishes into darkness. These cosmic enigmas serve as reminders that the speed of light is not a trivial feature, but the key that unlocks the most profound mysteries of reality. Through all of this, what emerges is a clear truth. The speed of light is not simply the pace of photons zipping across the vacuum. It is the rhythm of spacetime itself, the heartbeat of the universe, the constant that defines the geometry of reality and sets the rules for cause and effect. Light does not just move through spacetime, it is spacetime that shapes its movement, and in turn, light reveals the structure of spacetime to us. This mutual relationship is why physicists say that light's speed is not a property of light alone, but of the universe as a whole. When we talk about the speed of light as a limit, one of the most important concepts to understand is the role of energy. Energy is what allows motion to begin, what sustains it, and what resists it. When an object is forced to move faster and faster, for objects with mass, there is a fundamental barrier that makes reaching the speed of light impossible. This barrier is not just practical, it is built into the very laws of physics. It is a wall made not of stone or steel, but of energy itself. To imagine this barrier, think of trying to push a boulder up a hill that never ends. With every step, the hill grows steeper. The harder you push, the more effort is required, and though you can get closer to the top, you can never quite reach it. This is the situation for anything with mass as it tries to approach light speed. At the root of this lies Einstein's theory of relativity, which tells us that as an object accelerates, its energy of motion, or kinetic energy, grows. At ordinary speeds, the increase is modest and matches what Newtonian mechanics predicts. But as the object gets closer to light speed, relativistic effects begin to dominate. The energy required does not grow linearly, it grows dramatically, climbing steeper and steeper as velocity increases. Mathematically, this is described by the Lorentz factor, which shows how time, length, and energy change as speeds approach the speed of light. The closer you get, the larger the factor becomes, heading toward infinity as the object nears light speed. What this means in physical terms is that to accelerate a particle with even the tiniest bit of mass to the speed of light would require infinite energy. Infinite energy is not something the universe can supply. Even if you harnessed all the energy of the stars, all the power in the galaxies, it still would not be enough. This is the energy barrier. It is not a limitation of our technology, though technology certainly faces its own limits. It is a limitation of reality itself. Woven into the structure of spacetime and the conservation laws that govern energy and momentum, this energy barrier is not just theory, it has been tested again and again in the laboratories of particle physics. At facilities like the Large Hadron Collider in Switzerland, scientists accelerate protons to speeds incredibly close to that of light. These protons carry enormous amounts of energy, and the closer they get to light speed, the harder it becomes to add even a fraction more velocity. Instead of their speed increasing significantly, the added energy shows up as an increase in mass energy, making the particles behave as if they were heavier and harder to push further. Even at 99.999999% of the speed of light, the protons are still shy of the ultimate barrier. No matter how much energy is poured into them, they will never reach the actual speed of light. The experiments confirm what relativity predicts. Massless particles like photons can move at light speed, but anything with mass cannot. This barrier has profound consequences for how the universe functions. It ensures that there is a cosmic speed limit, a maximum rate at which information, matter, and energy can be transmitted. Without it, the universe would lose its order. Imagine if particles could leap past the speed of light. Information could arrive before it was sent, cause could follow effect, and paradoxes would unravel logic itself. The energy barrier is what enforces the law of causality. It is what ensures that time flows in one direction, that signals travel in an orderly fashion, and that the universe remains consistent rather than chaotic. It is also important to realize that the barrier is not about friction or resistance in the ordinary sense. In space, far from planets and stars, there is no atmosphere to slow an object down, no medium to resist its motion, yet the barrier remains. It is not about obstacles in the path, it is about the relationship between mass, energy, and velocity itself. The laws of physics dictate that energy and momentum are conserved, and relativity dictates how they behave as speeds climb. The result is that infinite energy would be required to push mass through the wall of light speed. No clever engineering, no futuristic propulsion system can bypass this law. Even the smallest particles teach us about this barrier. Neutrinos, for example, are incredibly light particles that stream through the universe, passing through stars, planets, and even our own bodies with hardly any interaction. They travel very close to the speed of light, but because they still have a tiny mass, they remain just under the limit. There was once a controversial result suggesting neutrinos might have been measured moving faster than light, but later experiments corrected the error, and the barrier remained intact. Every particle studied, every experiment conducted, has confirmed the same conclusion. The energy barrier stands firm. The implications of this barrier extend into cosmology, the study of the universe as a whole. The expansion of space itself can carry galaxies away from one another at effective speeds greater than light, but this is not because matter is moving through space faster than the barrier allows. Instead, it is because the fabric of spacetime itself is stretching. Locally, the energy barrier still holds. No particle, no signal, no spacecraft can exceed the speed of light relative to its local spacetime environment. This distinction highlights how the barrier is not just about objects moving in space, but about the geometry of space and time itself. For humans dreaming of interstellar travel, the energy barrier is one of the greatest challenges. At sublight speeds, the distances between stars are immense. Even reaching the nearest star system, Proxima Centauri, would take over 4 years at light speed, and far longer at achievable velocities. The energy demands of even approaching light speed for a spacecraft with significant mass are staggering, far beyond what our current technologies can provide. This is why concepts like generation ships, suspended animation, or hypothetical shortcuts like wormholes and warp drives capture so much imagination. They represent ways of exploring the stars without trying to brute force our way through the energy barrier. Yet, as of now, the physics remains clear. Accelerating mass to the speed of light itself is impossible. The energy barrier also gives us insight into why photons, the particles of light, are unique. Because they have no rest mass, they are not bound by the same rules. They are born moving at light speed and remain there forever. They do not require energy to maintain this motion, it is part of their nature. This contrast between massless and massive particles underscores the importance of the barrier. It is not arbitrary. It is the dividing line between two categories of existence, between the carriers of light and information and the material objects that make up stars, planets, and people. In technology, the consequences of the energy barrier show up in subtle but significant ways. Particle accelerators consume enormous amounts of electricity, entire power plants' worth of energy, to push tiny particles closer and closer to light speed. Yet despite this colossal input, the particles never cross the line. This is why these experiments are not just about probing high energies, they are about confirming the very foundations of relativity. Each acceleration, each collision, reaffirms that the energy barrier is real, unbreakable, and essential to the coherence of physics. For a US audience, the story of the energy barrier is one with national connections. Much of the work in particle physics, from the early accelerators at places like Fermilab in Illinois to modern collaborations at CERN that include American scientists, has centered on exploring the high-energy frontier. The pursuit of pushing particles closer to light speed has been a driving force in physics, and American researchers have played a leading role in probing the mysteries of matter, energy, and the universe through these experiments. The barrier has shaped not only the laws of physics, but also the course of scientific discovery itself. The energy barrier is one of the universe's most elegant safeguards. It tells us that light is not just fast, but fundamentally special. It reminds us that mass and energy are deeply connected, and that the speed of light is more than just a number. It is the threshold that defines what can and cannot move through the cosmos. It sets the stage for the dance of particles and fields, the unfolding of stars and galaxies, and the ultimate order of cause and effect that shapes our reality. The universe operates with laws that appear both simple and profound. Among these laws, few are as striking and mysterious as the rule that nothing can move faster than light in a vacuum. This rule is not simply a scientific curiosity, not merely an equation written on a chalkboard. It is a principle that underpins the structure of reality. The speed of light, roughly 186,000 miles per second, is not just the pace of a photon racing across the cosmos. It is the boundary line that defines how space and time interact. To call it a speed limit is accurate, but it is also something deeper. It is the ultimate regulator of how cause and effect are linked, how messages are sent, and how the past flows into the future. It is the cosmic law that ensures the universe behaves in an orderly and comprehensible way. To understand why the speed of light is the universal limit, we need to picture what would happen if it were not so. Imagine sending a signal to someone across the galaxy faster than light. That signal would not simply arrive early. In some reference frames, it could arrive before it was sent. Cause would follow effect, and the arrow of time itself would bend backwards. Reality would become paradoxical, with events occurring in reverse order depending on who was watching. The law that cause precedes effect, which feels so natural to our daily lives, would collapse. By setting the speed of light as a limit, the universe prevents these paradoxes. It ensures that time remains consistent for all observers, no matter where they are or how fast they are moving. This universal speed limit is not just for light. It applies to every form of energy, every piece of matter, every ripple of information. Photons happen to move at this speed because they are massless, but the law extends far beyond them. The limit is not about light itself, but about spacetime. Light simply reveals the rule because it always travels at the maximum allowed rate. When physicists say nothing can move faster than light, what they really mean is that nothing can outrun the causal structure of the universe. Nothing can move faster than the unfolding of spacetime itself. For those of us on Earth, the idea that light has a speed limit may feel abstract, but its effects are woven into everyday technology. The Global Positioning System, GPS, relies on signals that move at light speed between satellites and receivers on the ground. The precise timing of these signals must account for relativity, ensuring that the measurements remain accurate. Without the universal speed limit, without the predictability of light's pace, systems like GPS would not function. Telecommunications, astronomy, and countless scientific measurements depend on this law. It is not only a principle of cosmic order, but also a foundation of modern civilization. When Einstein showed that the speed of light is constant and absolute, he reshaped our understanding of the universe. Before relativity, it was natural to assume that speeds added together. If you walked inside a moving train, your pace combined with the train's speed relative to the ground. But light does not behave this way. Whether you are moving toward it, away from it, or standing still, you will always measure its speed as the same. This invariance is at the heart of relativity, and from it flows the conclusion that no information or object can surpass that rate. The cosmic speed limit is not a matter of convenience, it is a direct result of how the universe knits space and time together. The consequences of this speed limit are profound in astronomy. When we look up at the night sky, we are not seeing stars as they are now, but as they were when their light began its journey. The light from the sun takes about 8 minutes to reach Earth. Light from the nearest star system takes over 4 years. Light from distant galaxies can take billions of years, carrying with it images of the early universe. The speed limit transforms the sky into a time machine, letting us look backward into cosmic history. It also means that there is a horizon to our vision. Beyond a certain distance, light has not had enough time since the Big Bang to reach us. The cosmic speed limit defines what we can see and what remains forever hidden. This law also sets the scale for communication across the cosmos. If humanity ever sends spacecraft to the stars, or if civilizations elsewhere attempt to reach us, their signals will still be bound by the speed of light. Even with the most advanced technology, interstellar messages would take years or centuries to cross the void. The cosmic speed limit ensures that the universe is vast not only in space, but in time. The stars may be close in the tapestry of the night sky, but in the ledger of communication, they are separated by gulfs that can never be bridged instantly. The speed of light enforces patience, reminding us that the universe operates on scales far beyond human lifespans. One might ask, why is the speed of light what it is? Why this number, neither slower nor faster? Physicists describe it not as an arbitrary figure, but as a natural consequence of the electromagnetic properties of the vacuum. The constant we call c emerges from the relationship between the electric permittivity and the magnetic permeability of space itself. It is a property of the vacuum, the empty stage on which all of physics plays out. In this sense, the speed of light is not just about light, it is about the very nature of emptiness. The way energy and fields propagate through the fabric of existence. When we call it a speed limit, we should be clear. The universe does not issue traffic tickets for breaking it. Rather, it is a boundary woven into the geometry of spacetime. It is like the edge of a map where there simply is no road to travel. No force, no amount of energy, no clever engineering can carry us beyond it. Every attempt to push closer simply requires more and more energy, until infinity itself is demanded. The limit is not arbitrary, and it is not negotiable. It is absolute. This absoluteness does not stop people from imagining what it might mean to bend or bypass the limit. Concepts like wormholes or warp drives, popular in science fiction, are attempts to explore whether spacetime itself can be reshaped to allow shortcuts. These ideas do not propose exceeding the speed of light locally, but instead altering the geometry of spacetime so that distances shrink or paths bend. Whether such things are possible remains an open question in theoretical physics, but they serve as a reminder of how deeply the cosmic speed limit shapes our imagination. We cannot simply ignore it, we must work around it. The speed limit also has a poetic quality. It ties together every point in the universe, synchronizing them through the constant hum of causality. It ensures that events unfold in an order that can be understood, that history has a direction, that signals flow forward rather than backward. It is the metronome of the cosmos, setting the beat for the dance of galaxies, stars, and particles. Without it, reality would not simply be different, it might not make sense at all. For people in the United States, as with people everywhere, the cosmic speed limit has been part of the cultural imagination for generations. From Albert Einstein's fame in the early 20th century to the space race that defined much of the Cold War era, the idea that light sets the universe's fastest pace has fascinated and inspired. It appears in classrooms, science documentaries, science fiction, and national conversations about the future of exploration. American scientists and engineers, working in universities, NASA, and research labs, have contributed immensely to our understanding of how this law governs the cosmos. The speed of light is not just a number in physics, it is part of the shared human journey of curiosity and discovery. As we reflect on this universal boundary, it becomes clear that light's speed limit is more than a scientific rule. It is a safeguard of consistency, a horizon of knowledge, and a reminder of the scale on which the cosmos operates. It is what allows stars to shine across the night, what lets galaxies remain distant and distinct, what ensures that messages move forward in time. It is not merely about light, it is about order itself, about the universe's commitment to coherence, about the way space and time themselves are stitched together. Speculating about the laws of nature is an exercise in imagination that often reveals why the rules are the way they are. One of the most striking thought experiments in physics is to consider what reality might be like if light had no limit. If photons could travel at infinite speed, or if there were no maximum speed at all, the universe would unfold in a way that is radically different from the one we inhabit. This is not just a playful question, it is a serious reflection that helps us understand the role the speed of light plays in holding the cosmos together. By stripping away the rule, we expose the scaffolding it provides. Imagine for a moment that light had no limit. In such a universe, communication could be instantaneous. A person on Earth could send a signal to a colony on a planet orbiting a star thousands of light years away, and it would arrive immediately. The night sky would no longer be a window into the past, because the light from distant stars and galaxies would reach us instantly, revealing them as they are now rather than as they once were. Astronomy, as we know it, would not exist. The deep time we glimpse when we look into the heavens would be erased. Instead of seeing galaxies as they were billions of years ago, we would see them in real time, their current states laid bare to us. The romance of starlight carrying ancient stories across the cosmos would vanish, and with it, our sense of connection to cosmic history. This removal of delay might sound like a gift. Who wouldn't want to see everything as it is? To speak across vast distances without waiting years or centuries for a reply. But the consequences run deeper, and they are troubling. If light had no limit, then information itself would have no restriction. Signals could be transmitted instantly, and depending on how one moves through space, those signals could even arrive before they were sent. The principle of cause and effect would begin to unravel. Time's arrow, the idea that causes precede effects, would lose its meaning. You could imagine sending a message to the past, altering events before they even occurred. The logical contradictions this would create are not small inconveniences, they would threaten the very coherence of reality. Consider what it would mean for physics itself. The constancy of the speed of light is the foundation of relativity. Remove it, and the whole structure of spacetime would collapse. Without a maximum speed, the very geometry of the universe would shift. Distances and durations would no longer behave in consistent ways. There would be no universal limit binding observers together, and the laws of physics might differ depending on perspective. Relativity would no longer unify time and space into a coherent whole. Instead, the universe would become a patchwork of conflicting experiences, with no guarantee of consistency between them. Another profound consequence would be the loss of causality as a safeguard. In our universe, the speed limit prevents paradoxes. It makes sure that no effect can precede its cause. But if information could travel instantly, paradoxes would proliferate. Imagine preventing an event before it happens, or triggering an effect without a cause. The logical backbone of the universe would twist into knots. Physics thrives on consistency. Remove the speed limit, and that consistency could collapse into chaos. The fabric of spacetime would also change in a universe without a speed limit. Our understanding of time dilation and length contraction depends on the constancy of light speed. Astronauts traveling near light speed experience time differently from those at rest. This is not a bug, but a feature of relativity. It keeps the universe fair, making sure that no one reference frame is more privileged than another. If there were no speed limit, then these relativistic effects would vanish. Time would tick the same everywhere, regardless of speed, and distances would not contract. On the surface, this might sound like a simplification, but it would strip away the very framework that ties space and time together. Spacetime as a unified entity would dissolve, and with it, the elegant geometry that governs the cosmos. Energy, too, would behave differently. In our universe, the closer an object gets to the speed of light, the more energy is required to accelerate it further, eventually tending toward infinity. This is the barrier that makes light speed unattainable for mass. Without a speed limit, this barrier would not exist. Particles with mass could accelerate indefinitely with finite energy. The balance between mass, energy, and motion would collapse. Conservation laws that depend on relativistic principles would need to be rewritten, and the universe might lose its stability. The orderly interactions of matter and energy would be replaced by unbounded accelerations and uncontrollable dynamics. There is also a human dimension to this speculation. If light had no limit, our perception of reality would change in ways difficult to fathom. Right now, when we look at the moon, we see it as it was about a second ago. When we watch a distant supernova, we are witnessing an explosion that happened millions of years ago. This delay gives us perspective. It connects us to cosmic history and reminds us of the vast scales of the universe. Without it, we would be cut off from that history. Everything would collapse into a present moment that is immediate but shallow. The sense of scale, of distance, and depth would evaporate. The universe would feel smaller, less majestic, stripped of its temporal grandeur. Culturally, too, the absence of a speed limit would shift our narratives. Much of science fiction is built around the challenge of crossing the light speed barrier, of finding creative ways to explore the stars despite the vast distances. Without that barrier, such stories would lose their tension. Space travel would become trivial, communication instantaneous. The drama of exploration, with its blend of limitation and possibility, would dissolve into simplicity. Yet, in that simplicity, something would be lost: the very struggle that makes discovery meaningful. From a cosmic perspective, galaxies themselves might behave differently if there were no speed limit. In our universe, the speed of light interacts with the expansion of space to create horizons, regions we cannot see or influence. These horizons define the observable universe and shape the structure of cosmic evolution. Without a speed limit, horizons would not exist. Every part of the universe would be connected to every other instantly. No matter how far apart, the universe would lose its regional character, its layered unfolding. Instead, it would become a single, simultaneous whole. While that might sound appealing, it would erase the very conditions that allow galaxies, stars, and planets to form in the way they do. Locality, the principle that things influence each other through finite signals, is essential to structure. Without it, the universe might collapse into homogeneity, flat and uneventful. Even quantum physics would be transformed. One of the great mysteries of the quantum world is entanglement, where particles share states in ways that seem to transcend distance. Yet even here, the no-signaling principle, the rule that entanglement cannot transmit information faster than light, keeps the theory consistent. Without a speed limit, quantum systems could transmit information instantly, breaking the careful balance that prevents contradictions. Quantum mechanics and relativity are two pillars of physics that, though not yet unified, rely on the constancy of the speed of light. Remove that constancy, and both pillars would crumble. It is worth noting that some physicists and philosophers have speculated about hypothetical particles, such as tachyons, that could travel faster than light. But even in these speculations, the paradoxes and contradictions they introduce are formidable. Tachyons, if they existed, would destabilize causality. Their presence would imply a universe where the neat progression of time is undermined, where effects can ripple backward, and where physics as we know it loses its predictive power. The fact that we do not see tachyons in experiments is consistent with the idea that the speed limit is real and necessary for people in the United States and around the world. The fascination with faster-than-light travel is often tied to dreams of exploration. Science fiction franchises imagine warp drives, hyperspace, and other means of leaping beyond the barrier. These stories resonate because they highlight the enormity of the challenge and the ingenuity required to overcome it. If light had no limit, such dreams would be unnecessary. Yet in their absence, the narrative of striving, of pushing boundaries, would be diminished. The cosmic speed limit gives us something to reach for, even if it cannot be surpassed. It shapes our imagination, our storytelling, and our sense of possibility. Ultimately, the speculation about a universe without a speed limit shows us why the one we inhabit is so carefully structured. The limit on light's speed is not a hindrance, not an arbitrary restriction. It is a safeguard, a framework, a principle that allows time to flow, matter to form, and history to exist. Without it, reality would lose its coherence. Time would unravel, causality would collapse, and the cosmos would become unrecognizable. One of the most frequently discussed possibilities is the idea of wormholes. In Einstein's general theory of relativity, spacetime is flexible, capable of bending and curving under the influence of mass and energy. Just as a sheet of fabric can be folded to bring two distant points together, spacetime too might be manipulated in ways that shorten the path between far-off regions. A wormhole, in theory, would connect 2 points in spacetime through a tunnel, creating a shortcut. Travel through such a tunnel would not involve moving faster than light locally, but the effective distance traveled could be reduced dramatically. Instead of taking thousands of years to cross between stars, a journey might take minutes or hours if such a passage could be stabilized. The concept is tantalizing. Though our current understanding suggests enormous obstacles, exotic matter with negative energy density may be required to keep the wormhole open, and no evidence has yet shown such matter to exist. Still, wormholes remain a symbol of what could lie beyond the limit, a loophole hinted at by the equations themselves. Another mystery arises in the realm of quantum mechanics, specifically in entanglement. When two particles are entangled, their states become linked in a way that transcends distance. Measure one, and the other responds instantly, no matter how far apart they are. To the human mind, this looks like faster than light communication, but the reality is subtler. Entanglement cannot be used to transmit usable information faster than light, because the outcomes are random till compared through classical means. Yet the instantaneous correlation remains, defying our classical intuitions. Einstein himself called it spooky action at a distance, and though experiments confirm the phenomenon, its implications remain puzzling. Some physicists wonder whether entanglement hints at a deeper layer of reality, one where information may be shared across space, without the constraints we currently recognize. If so, it may one day open doors to new principles that redefine our understanding of the light speed barrier. The idea of warp drives touches on this possibility. In the 1990s, physicist Miguel Alcubierre proposed a theoretical model in which a spacecraft could remain stationary within a warp bubble while spacetime contracted in front of it and expanded behind it. To an outside observer, the bubble could appear to move faster than light, while inside the ship, no rule of relativity would be broken, because the craft itself never moves faster than light relative to its local spacetime. The challenge, again, lies in the requirements, staggering amounts of energy and negative energy densities beyond anything we can create. But the model demonstrates that the laws of physics, as written, do not entirely forbid the manipulation of spacetime. They merely remind us of the extraordinary scales of energy and ingenuity required. As we bring this journey to a close, let us pause and reflect on the path we have taken together through the mysteries of light and its cosmic speed limit. From the simple yet profound realization that light does not travel instantaneously, to the intricate mathematics of relativity, to the speculative frontiers of wormholes and warp drives, each keynote has been a step deeper into the heart of one of nature's most fascinating truths. The speed of light is not just a number written in textbooks, but a boundary woven into the fabric of the universe, a law that shapes the way time flows, the way distances stretch, and the way causality holds the cosmos in balance. But in the end, the light speed limit is not a frustration, not a wall meant to hold us back. Instead, it is a compass, pointing us toward the vastness of what remains unknown. The fact that light travels at nearly 186,000 miles per second is not just a measurement, it is a reminder of how immense the universe truly is, and how humbling it feels to live within it. It is a gentle nudge, reminding us that our quest for understanding is endless, that science is as much about questions as it is about answers. For an American audience and for people everywhere, this journey resonates with the same spirit that has always driven human beings: the urge to explore, to imagine, to reach beyond what seems possible. Just as generations once set out across oceans and continents, just as astronauts once set foot on the moon, so, too, will future explorers look to the stars with curiosity, dreaming of what might lie beyond the horizon of light. And as you settle now into rest, think of this truth, not as a barrier, but as a lullaby whispered by the cosmos. The speed of light is the heartbeat of the universe, steady and constant, shaping the rhythm of time and the melody of space. It reminds us that even in limits, there is beauty. Even in boundaries, there is wonder. And within every mystery, there is the invitation to dream.